just legal. So we're here just trying to say that we don't always know everything from Battelle's, and but we try our best and put in the most effort that we can with what we have in the data we collect. And a lot of these assumptions and the predictions in this presentation for Battelle's and its clients cannot be held reliable moving forward. That's all. I'm done with it. And moving forward, it's really I'm really happy because I used to be you guys. I was in my grad school, and every time somebody brought up a departmental seminar or conferences, the first thing that came up to my mind is, will there be food there? You know, if the talk is good, or if not, talk is not so good, the food won't be there, and it will compensate my times. Anyhow, thank you for showing up again. For a summary, I'm gonna be pretty straightforward here. For you guys, petroleum engineering majors, and CCUS play an important role in reducing our carbon footprints because of the 45Qs have been put in place, and a lot of our clients are small ethanols or biodiesels plants, even coal power plants are considering going into the classics permit because they have that 45Qs. It's just kind of like they give you a free lunch and then to make you go through stuff. But at the same time, you guys as petroleum engineer majors can play a role in all this work because you are still a key person across the various stages of the process, which I will talk about briefly after this. So a lot in my line of work, a lot of time the model boundary can have a significant impact on the prediction of injectivity, and it means money, right? So a lot of our clients are in this for the economical benefits that they receive through the 45Q tax credit. If you don't already know what it is, and so the more you can inject, basically, I think it's at $85 per metric tons right now for 12 years. Hopefully, they'll extend this amount or for a longer period of time, or make it even more attractive by increasing the dollar amount going forward. But that's still in the work. In order to achieve that, you have to turn in a permit application successfully to drill that wells and complete it and actually inject. And in the permitting process, the EAR delineation is a vital part of that classics permitting process. But how and what is required is still a learning process. I was at SBE the other day in Louisiana, and there was a talk about boundary conditions, and folks from the EPA were right there asking questions. I kind of go to shows that not always, even from the regulating perspective, they don't always have the expertise or most up-to-date knowledge to regulate or enforce the classics permit properly. We don't know yet, and they don't know yet. So we're in a learning process for this, obviously. Before I move forward, I'm just gonna really quickly mention Battelle's. Probably a lot of you haven't heard. We're based out of Columbus, Ohio. We've been here for about 90 years, involving a lot of national security, environmental, and mainly national lab management. I came from, during my PhD, I worked mainly for Los Alamos, and I came directly from Los Alamos to Battelle's because the Los Alamos was part of the lab management program that they have there. So moving forward, Battelle has about 11 billion in annual revenues. We have managed a lot of national laboratories across the country. There are about 9. We have about 3,000 patents dates, and especially we have a lot of people with advanced degrees. So, for example, my team as reservoir engineers, for my team, we all have PhDs. So you won't feel alone as lonely as grad student coming from say UT Austin into Battelle because we have a highly educated workforce. Again, we manage a lot of the national labs, and Los Alamos is where I came from right after my PhD. Also, we have evolved from managing a lot of the earlier government initiative to launch CO2 sequestrations. Some of the Midwest Carbon Sequestration Partnership, for example, I did work for the U.S.-China projects in the Oros Basin in China. There's carbon safe projects across Nebraska, Kansas, Ohio, and there's also I've heard this effort going down there at the offshore carbon storage project. So there's many efforts going on at the same times, and we've been around for quite a bit of time with the early government-funded CCUS program. So I'm gonna go straight into the roadmap of a CO2 sequestration projects. What do we play? What role does an engineer play here? Usually at the first step of feasibility, we call it phase one, or I don't know whatever you call it. It's a feasibility study where we gather any geological information for regions. Really, at that point, we're just trying to identify any major red flag for our projects. And your role, for example, as a reservoir engineer, is to bringing your skills in simulation and build a tank model, a layer cake model, to inform your clients if they need any land management. Like if they have a small property, will they need to go talk to landowners around their surrounding landowners and acquire more land, forest space, right, in order to inject CO2, that sort of things. And so engineers are involved really early on in this process, and maybe identify any legacy wells in the area that will probably make the projects economically not viable, that sort of things. It's not just geologists who are doing the work in the exploration phase, if you could call it that. And going to from that feasibility, we go into the design, characterization, and permitting, which is where I'm at right now. I spent a lot of my time reading up on a lot of the permit application that have been approved or are under review right now. And I'm also planning a lot of drilling wells because we need mini fracs tests. We need mini fracs step rate tests. We also need MDT, so on and so forth, in order to gather the information we need from our on-site well. So that is definitely helpful. I'm also reviewing permit application models from other teams within this company, and then we'll make sure that it's technically sound before we ship it out to the client for even further evaluation. So working in this environment, you'd be meeting a lot of people outside of your expertise. I've been talking to a lot of drilling engineers, a lot of completion folks, production, even land management. They want to know how big is a plume, for example, that they need to purchase land for around their properties. And then obviously, when you go into constructions and operations, that's where you have lower uncertainty, but the costs start increasing. Then you get into optimization to minimize costs and inject the most out of your wells, maybe one or two, in order to make your company the most profits. Pretty similar to oil and gas, right? But it's the biggest thing is I guess I would say is the legal challenge that we have with permit applications, because when I signed up for petroleum engineering, I didn't imagine myself dealing with legal this much. And like I said, we talk to land people, we talk to EPA in order to figure out what they want for their particular regions. For example, region 5 or 6. 5 is where we operate, and 6 is down south where you guys are, Texas, Louisiana, that sort of things. So for CO2 storage, why it's preferably we want it to be in supercritical because it only occupies a small volume versus in gas phase. It's a lot harder to monitor gas CO2 than supercritical. So you want it to be in a small volumes in a certain depth windows, like at least 2,600 feet below the surface. That's where usually that's a gold standard or go-to number where we consider CO2 projects for injections. Supercritical. That's where, yeah. Okay. After this, we're gonna go next to this is the key point we usually bring up to our clients or stakeholders for a feasibility studies. These 5 main factors are reservoir capacity, injectivity, and confinement and containment. Usually, your reservoir engineers are involved with injectivity testing, where say we pick a lot from a public database. We have a petrophysicist run the lot calculation, determine average porosity permeability, and then I'm going to put in two layer cake models and estimate what injectivity they could be expecting, and then estimate also the lateral extent of your plume in order for land people to be able to go out there and figure out how many landlords they need to talk to, for example. Sometimes we're also involved with the containment part, not as much as geophysicists because they're dealing with faults more often. You may be lucky to have a line of maybe a 2D line or 3D lines run through your areas. That's probably more common down in Texas, but not up in Region 5, for example, or in California. Yeah. So you also reservoir engineer could go out there and look up legacy wells that may be serving as potential pathway for CO2 leakage, and that is when your clients may have to go out there and remediate those wells which were drilled and completed way back in the 60 or 50, where the standard was not as rigorous back then and it is now. So if we look at these 5 categories and we identify no red flag, we'll move the project forward. Doesn't mean the project is a slam dunk, but it means that it's okay to move forward at this point until we get more data. Okay, no questions. By the way, feel free to ask questions if you have any. Subsurface data, yes. We have wall log data, as I was chatting with Nadia earlier. We run the standard combo test with the normal curves, and then it'd be nice to have NMR to verify permeability. Sometimes most likely we'll have pores, conventional core, and then if we don't get that, if you do drills and you have your formation is too unconsolidated, we may get sidewall core to supplement that information. And obviously we need seismic data. Usually for a phase 1, we don't go out there and get seismic data on our own, but we license existing data that are already in the area. So this is pretty standard stuff for explorations if you were to work in an oil and gas in the company. integration and evaluations. I'm not a geologist here, but you try to go over this really quickly. We combine all of the regional and the local data that we have access to. At this point, we don't really do much acquisition yet until we drill that wells. So we rely on publicly available data. So company like TGS or the state surveys, any database out there that we could um, license or purchase data from, that we put together the models that we need for our next step in the modeling process. It's just pretty standard stuff. You get build a depositional model and put everything in your static earth model and then run your simulations. All the again, this is to identify any red flags for the projects. If it's more, we're trying to kill the project essentially, because if we don't and we wait until clients already put in multi-millions dollars investment into these projects and it doesn't work, and there will be a hard conversation to have because of some of the red flag we may not be able to identify early. So it is really a challenge for us to identify any early red flag for the projects, and sometimes those red flag could be from nearby injection well, like if you have a wastewater injection operation nearby and you don't know about it, and you just don't know about it. I mean, if there's no access to data, then there's only so much we could do, but we always try to do our best. For example, the models we built here is from a talk that we give in Canada last year's from one of my teammates went and gave a talk. It's basically going through the conceptual modeling part of bases, then you populate your porosity and permeability models accordingly. You can kind of tell that a lot of the formations we're looking at are sandstone, so we have a lot of fluvial channels, and they are directional. So if you can look at that, it's gonna show you that this is a east-west fluvial channel model that we're modeling here. So it's basically in the middle here, we're showing a map view. So it's kind of follow along with that where that channel is, and it really also dictates where your AOR is going to be, because where your CO2 plume propagates, right? It's where your pressure front is going to follow as well. Okay, yeah, this is just an example area review for the red trail permit from North Dakota. So you can kind of see the CO2 plume. You can see the CO2 plume here, which is purple, and the area of review up here is the orange line here, is defined in the permit. That is the pressure front, and it's basically defined by pressure cutoff called the critical pressure threshold. The EPA guidance is that what is the minimum pressure that will push the brine upward imaginary. Let's say if there's a wellbore in the area that you know nothing about, and then what is the minimum pressure delta P that it will take to move the CO2, the brine, your in situ brine up through that wellbore into a USDW. That would be your delta P for this AOR determination. So your client or our client is responsible for the wells, any legacy well in this area, and it's the defined definitions of the AOR. It really matters because it determine how much money your clients basically have to spend in order to remediate any wells that they know about in the area. So it's inter so in addition to injectivity, AOR play a major role in the project economics. And also we have after that, after you define the AOR, you put in place a monitoring plan, right? Because the EPA requires you to not have any leakage for the USDW, making sure that you're not endangering drinking water. So requires subsurface monitoring by wells and other methods to detect CO2. So we use a multitude of technology in order to, to detect any CO2 or brine leakage early on. And this is still work in progress and moving forward. And the permitting process is really what I'm at right now. A lot of times the EPA would approve certain permit and not others. So some of the permit that I've looked at don't they didn't. I don't want to say they're bad necessarily, but they really did the bare minimum and got through. And some others are they didn't really put in a lot of effort and didn't go through. So I don't. It's really a learning process to me and our team because it varies so much by third-party reviewers, region by regions, and whatnot. But it usually takes up to about a year or two in order to get it pushed through. Well, for drilling operations, that also goes into the permit application because if you have on-site data, it's more it's easier to convince the EPA that you know what you're talking about the subsurface at your site. Like I said, we're working with drilling engineers. We're working with our petrophysicists to pick the intervals that we're going to collect our data. And this is not cheap for our clients. It's about $3 to $5 million, and if you're talking about like small ethanol plants or biodiesel fuel plants, so it's a big investment, and they're not the ExxonMobil or Chevron, so it's their concepts of uncertainty and risk is relatively different from all those big E&P companies. And so after that, if you get lucky and go through all these processes that put in place by the EPA, you get to inject CO2, and this is really just a schematic of the wells and where we actually um, isolate this injection intervals and then push the CO2 out. And interesting, in one of our projects, we actually run into there's a critical depth that when you CO2 rises above that depth, it actually turns into liquid, and we haven't been able to find any regulation that said you cannot let your CO2 turn into liquid. But at the same time, it may create some additional challenge for your monitoring plan. Um, we still don't know what best to monitor that yet. We're learning it, so it's there are certain places where the reservoir is shallow enough that it's become a concern there in terms of injection. Okay, you guys, have any of you guys heard of ADM in Illinois?
No.
Probably not too many. That's fine. That's probably the first pioneering CO2 sequestration facility that started out injecting CO2 into the ground. It was recently cited for EPA violations of federal law because of the leakage. And I think I haven't heard directly from them, but what we interpret from the press release that it gave out is because the CO2 or brine was going through a degraded casing. One of the quality of the casing they put in there was not sufficient to keep the CO2 from leaking upward, and so they now have to having to suspend their CO2 injection operations and go in there and do more remediations as a result. But we'll find out what we learn about in the next steps and how the EPA will react for this kind of leakage and moving forward, because this is one of the very first projects that we're ever having to deal with this casing problems. Okay, before I keep moving, any questions so far? Sorry if I speak a little too fast or.
No, we are good, Min. We will have the like maybe questions by the end of the session. We are good.
Oh, okay. Okay, yeah. Either you ask question now or at the end, that's fine too. So I presented a talk earlier, a poster earlier at CCUS. I basically trying to build a tech models, right? Trying to check on different boundary conditions to see if it makes any difference in the injectivity predictions of the models. And see, for example, here the hydrostatic pressure gradient is usually from the MDT fracture pressure gradient is mini frac from the field. If you don't get mini frac, usually they do a step rate test um, to determine after they've run all the tool down there. Um, yeah, so these are pretty standard reservoir models, and we're trying to test if we inject with a small volume versus a bigger volumes, what it would looks like. So at a smaller volumes and shorter or even larger period of injections, the CO2 injectivity prediction doesn't diverge too much across all the volumetric, volume multipliers method or Carter traces or Feshkovich boundary conditions. Obviously, if you don't feel your boundary condition yet, it's not going to have a major impact on your injection prediction. But once you increase that significantly, it's going to be divergent across your injection scenario when you have a same model or even a bigger model when you inject the same rate of about a million tons per year, millions metric tons per year, then it's gonna you're gonna have a different injection numbers across these boundary conditions. And this is where we actually need to look into what to do about it, and it's an ongoing learning effort. And in my experience, I think volume multiply is a good method because it actually allow for better um, computer time. Because like if you're going to use Carter Tracy, it's going to slow your simulation time quite a bit. Or same thing with Feshkovich, and volume multipliers has more flexibility in terms of what to use and how many cells you want to use at the edge. There was a talk by another guy from Chevron, I think at SB this past month, that talks about gradually increasing the volume multiply instead of using just one row of blocks at your edge of the boundary. And this slide is basically showing, like I said, we're trying to change the number of the volume multipliers to see if we can use, instead of 10,000, we use 5,000 or 4,000. It's varying. That numbers also change the injection predictions. And so it has implication to our clients because if their plant is emitting, say, 400,000 tons per year, and we're predicting only, let's say, 350,000, and does that mean there will be economicals? I don't know, but it certainly has something to do with the boundary condition we had put in place. So it's really an ongoing area of work that we need to pay attention to. Again, I'm gonna go back to this slides and say you guys got a lot of future in this emerging business because we're drilling well back to back, and you guys as a petroleum or reservoir engineer can play a key role across different stages of the process. Even during feasibility, you're asked to do tank model already in order to see what injectivity your clients is getting and how much land they will need for their projects. Model boundary challenge is still there because it has direct implication to your injectivity predictions, and also the AOR delineation is going to be big because you want your clients to be be liable for the right amount of area that they need to do remediations or monitoring on. Otherwise, if your AOR is basically an infinite aquifer, it's going to be really hard to comply with the EPA monitoring regulations. And again, we're still learning in this process, but we'll try to figure out what we know best, and we can always, come up with corrective plans and move forward, if you will. So after this, I'll have another demonstrations. Right? Is that the plan, Nadia?
Yes,
After
we
the
are still
demo,
doing
I
that.
will
Yes.
have to open the floor to any questions.
Okay. So do you still have the demonstration part, or you will answer?
Um, I'll be a short one.
Okay.
So yeah, it'll be a short one instead. So I was thinking of showing you guys Pro and CMG, but and instead if we don't have that, that's fine. So this is the EPA method 1 and 2. Uh, EPA step 1 or method 1, then step 2 method 2. Um, when you have the strat columns of your injection zone at the bottom, you kind of see it early. Is to say your top depth of your formation is about 5,000 feet. That's more than 2,600 feet, and so it should be in supercritical state. And you have pressure at the top depth, brine density. Hopefully, it is really sailing down there because it's all the EP. I'm sorry, the AOR determination really depends on how saline your aquifer is, right? Because it will takes more energy in order to push that brine column up into USDW. So hopefully your injection interval is really saline. And when you move into this lowest USDW, you calculate a bottom depth, hopefully from your on-site well. So a lot of these calculation usually is done after you've drilled that on-site well because you can only do so much with a well 50 or even 20 miles away. Right? It may not be a problem in down south in Louisiana or Texas, but let's say in the Midwest or where elsewhere you don't have a lot of well coverage. It's the uncertainty is really big. So we usually we recommend our clients to drill that well and before we actually even go into the AOR calculation. Where we have the bottom depth here, with pressure there. Yeah, a lot of these pressure gradient has to be determined through MDT, and brine density is also from the on-site well. And if when you put in the numbers, it kind of goes through this calculations here, and all the equations are available publicly through the EPA. And if you calculate that delta P, the the amount of pressure difference it takes to move that column of brine into a USDW, assuming that there's a well bore that you have no idea existed. So if negative delta P here means overpressure for this particular example, it's not a real case, but it's the negative number here is just showing you that this is not in hydrostatic conditions. And if there were a legacy well that you don't know about, it will automatically flow into that USDW. So the EPA also give out another method two to calculate that delta P. And when you take that those parameters up here and put it down here, and take this number about 66 psi, and you subtract by the absolute of this method one numbers, you're left with about 46 psi in the end, and that's kind of chopped down on your pressure plume. So you basically take the pressure front in your simulation at the end of your injection, minus that with your initial pressure. You got the delta P, and then you're gonna filter that delta P out using this threshold of 46 or 47 psi here, and you get this. Hopefully, you get something similar to this AOR here, which is manageable and won't break the bank for your stakeholders, if that makes sense. Okay, so hopefully that covers it. Any questions you guys are interested in, and I'll try to answer. If I don't know, I'll come back with answers later on.
Yes, we do have questions. The first one's done.
Hello, man. It was a nice presentation, and thank you so much for here. My first question is related to reservoir characterization. Since the saline aquifers, they don't have any drill data, any logs, or any pressure transient data. So we usually, like in terms of the boundary conditions and also unknown reservoir characteristics such as reservoir system, the type of flow in the pores, and also that will help us in understanding the AOR and the plume migration over the time. And my second question is related to the observation wells. Since if there are some legacy wells and if there is no issue in the leakage, like we know that the casing is integrated and the cement is intact as well, so we can use those legacy wells as an observation wells for the plume migration. Did you get any chance to look into these kind of conditions? And also, my third question is like, what kind of modeling challenges have you faced while modeling the CCS and saline aquifers, especially in high saline aquifers?
Yeah. Can you repeat your first questions again?
Yeah, my first question is related to reservoir characterization. So this is not like a typical oil and gas field. Saline aquifers, we don't have too many wells drilled. We have very little information about the reservoir characteristics, type of pores, the type of flow within the pores, whether the different single porosity or microfractures, type of faults or type of boundaries we have, whether we have no flow boundary, whether we have a kind of permeability barriers or anything like. Yeah.
So how do we deal with the lack of data?
Yeah. How do we deal with this kind of uncertainty?
Yeah. So we have a uncertainty and risk matrix. I don't think I can show you but we evaluate your projects based on these criteria, right?
Okay.
Reservoir capacity, injectivity. For I guess I mentioned it somewhere in the talk that we rely on many publicly available data that we have,
Okay.
or any chance that we could lease data from, like, say, TGS or Embarrass,
Mhm.
or the state surveys. We gather information from those sources, and
Mm.
let's say we have our reservoir petrophysicists look at the logs and determine if there's the existence of a reservoir. If there's a map, like a regional map for salinity, it would tell you, what area laterally or on a map that you're likely to be at least 10,000 ppm per the EPA guidance.
Okay.
Yeah, so it's all publicly available data. We're not like the super major yet, where you have internal database for carbonate or sandstone reservoir. Yeah, but we do have our internal teams that work with the state surveys, or um,
Mm.
a lot of the locks companies that provide data that we could lease from. And so does that answer your first
Yeah,
questions?
yeah, pretty much. Yeah.
Yeah, so there's that relationship between uncertainty and risk, right?
Mhm.
Uncertain because we don't have the data, or we have low confidence in the data, but risk is something that could happen, right?
Yes.
And there has to be, they have to go hand in hand. You just cannot just identify uncertainty, but there's no risk.
Mhm.
So they have to be, looked at um, simultaneously. And and so your second question is for the
Legacy
have I
well.
looking for what monitoring wells?
Yeah.
Uh, Um, for monitoring well, particularly, I haven't had a chance to look at the legacy well bores yet, because at least in the region that I'm working on, a lot of them are really old, like 50 in the 50 and 60, and so back then, a lot of them are not even on papers, to be honest.
Yeah.
So they don't write it down on a note, or when you go into a state survey database, they don't know that even existed, or maybe it's just a well in somebody's backyard, so
Yeah.
on and so forth. So it's really hard to figure out what is like to what is the quality of the cement, or how long it would take for that cement to degrade. We don't always have any ideas, and that's why we need to do a really good job of quantifying that AOR, so that our clients are only liable for a certain area, right? Ideally, we want it to be as small as possible,
Yeah.
right? Smallest would be ideal, but that's not always the case.
Yes.
Um, and so we drill. The plan is to drill a monitoring well, and then probably would uh, do some testing, or
Mhm.
there's others technology from the monitoring team that I'm not familiar with, but they probably would do some surface survey in order to test out. The main idea here is to identify as many well as possible
Mhm.
before we even dive into the quality of cement, that
Right.
kind of thing. Yeah, and to answer your third questions, for what are the modeling challenges? Is
Yeah.
that
Yeah. That's my
Yeah,
next question. Yes.
there are many challenges. There are many challenges. For example, the other day I was running into a challenge of a really low permeability reservoir with low relative permeability as well. So we built a local grid refinement
Mhm.
around our wellbores, right? Because it will lower. Let's say we inject for about 30 years, but now clients have daily rate. It's not like we're injecting 1 million tons every day, or every single year. So for a bio or diesel or maybe a ethanol plant, they have to ramp that up over time. So you have to be able to model that accurately for the daily rate.
Yes.
So usually when we run simulation, we put annual rate, right?
Yeah.
For so to building that local grid refinement is really helpful for that early ramp up in the models. Yeah. But there was a case when we actually have really low permeability, really also low relative permeability around the wellbores, and
Mhm.
it actually hindered the flow. So initially we run the model, we couldn't meet the target rate,
Mm.
the rate that the uh, plan was putting out or emitting. Um, that we were scratching our head, something wrong here, right? And then we go back and forth a lot, and then eventually the solution was to expand that local grid refinement out so that the plume can actually extend out and it solve a problem. It
Mhm.
could finally meet the target injection rate and going above it a little bit, but it was difficult to justify to management why we were giving them one answer and now we're coming back and changing another answers.
Mm.
So yeah, that one too. That one is the first one. And another challenge is just the communication, right? A lot of our clients are not ExxonMobil. They're not familiar with the subsurface, and so they're not aware of all the details. And like if you let's say if your model injects more than 1 million tons per year for single wells, right? But that's only a layer cake model.
Yeah.
We're not comfortable of giving them that exact number. It could be 2 million, for example.
Yeah.
Some people would take that number and run with it. If you know what I mean,
Yeah.
they will they will cling on that numbers and they will say, hey, this is the number. You tell me why does it not injecting like this? Say we come to injection
Mhm.
stage, and so let's say we only we want it to be broad enough, but specific enough. Like if we when I tell a client, we would say, hey, your area has the possibility of injecting up to 1 million tons per year or a little bit maybe more,
Mhm.
but we don't want to give them the exact numbers so that they can kind of you know hold us accountable for that
Yes.
because at the end of the day it's a model and
Yeah.
as we gain more insight into the subsurface, we'll update the model
Yes.
just like an oil and gas
Yeah.
operation.
Thank you, Min. Thank you so much.
Yeah, appreciate it. Hopefully, I
Thank you so much, Min.
answered.
I do have a quick question. So, in the CCUS conference, I attended a presentation from Chevron from Dr. Yusuf.
Mhm,
He's a
mhm,
reservoir engineer at Chevron. He
mhm.
was talking about like regarding the boundary conditions. He was talking about considering like the volume modifier as graduated. Like he was started by
Yep.
low values, then up to like high values. Like, do you consider that in your simulations? And do you find this as like a beneficial way to deal with the boundary conditions? Like, to be honest, I do the modeling for the CO2 sequestration, but it's core scale. I tried both. I tried to have the last layer with a high volume modifier or
Mhm.
have a gradually increase in the volume modifier to toward the boundary conditions. What are your insights on this like regard?
So it really depends on the EPA. Like I said, I mentioned early in the model in the presentation. Sorry, the EPA sometimes rely on third-party reviewers, and they could be tough, they could be easygoing. I don't know. It depends. From what from the permits that we have submitted, it really depends on who is reviewing your permit. And so, but I think the EPA is eventually catching up to the fact that you cannot just use a single layer, or row of cells that go has like 100,000 um, more volume multipliers numbers. I guess that would make an entire Earth connected, for example. But so far we are not able to. We're working with CMG to to, to try to understand the gradual volume multipliers more. But in our standard practice, we're trying to use other techniques instead of just the volume multiplier, like say using a hardened grid in order to make the model really big. It was one of the permit application that the reviewer wanted us to really make the model super big, like hundreds of miles,
Mm.
um, by hundreds of miles. So
Yeah,
it it depends on. I wish I could give you like um like a universal answer, but
yeah.
I don't because it depends on who reviewers you're gonna get if you when you push these permit application through the system.
Yes, understood. Thank you so much. Any questions? I think that's
I
it.
have a question, please. Can you hear me?
Yes, yes,
Yeah.
sir.
So I'm just wondering about. I might have missed this earlier, but about the caprock. What was the properties you used for this caprock, and what do you think? What do you think the effect will be of optimizing those properties on the storage capacity that you will have in this model?
For the cap rock, we're trying to show the EPA. So when you drill that on-site well, you will have core, right? We usually core through the cap rock, and we'll send those core sample into say a core labs or any vendors out there um, to run the uh, entry capillary pressures measurement, and kind of convert that into CO2 measurement, and we use that pressure to prove to the EPA that hey, this is competent cap rock. So usually they require about 800 psi for that PC numbers, but a lot of our cores come back around 400, 500, even 600, and that's about the max that we could get to show them. And we'll probably will take it to the EPA and say, hey, this is what we have, and is this reasonable with the current data that um, is available in the industry. So
Uh,
hopefully that's
was it? Was the measurements done by MICP? The
MIC.
mercury and intrusion
Yeah,
pressure.
yeah, in
Yeah,
mercury, and then you
that's
convert them.
yeah. I'm sure you know that that's always give a rough estimate, not the exact value of the capillary entry pressure,
Yeah. So
and
you
usually it's a
also
lower value.
yeah.
But
So you do also we what we did is we also measure the contact angle to do conversion from of that into the
yes.
CO2 versus brine injection to answer your question.
So what was the permeability of the caprock in this model?
Permeability of the cab rock usually pretty low, like 0.001 millidarcy.
Okay.
So yeah, so you pick it out from the rocks, right? What interval
Yes.
your rock is really low, and then you run your sample based on that.
Okay. Yeah. Thank you. It's just that my point of this question is because it's not only the storage capacity does not mainly count on the mechanical part, which is the fracturing, but also count on the capillary part, where the permeability and the capillary entry pressure will play an important part in how much you can store underneath the caprock. Yeah. So
Yeah,
thank you so
there's
much.
yeah. The one thing I want to add is we don't always inject at the top of the injection intervals. Sometimes we inject way down there. So when you're done injecting, your CO2 plume, is still far from your cap rock. So it will, it doesn't even matters if it does matter to have a primary seal, but sometimes your formation have baffles in between, to to hinder your CO2 upward movement.
Thank you.
So, yeah.
Thank you so much, Min.